Okay, so we're back for second derivatives. So, like I just mentioned earlier, all we're doing here is differentiating the function twice. So again, in our notes book, just turn the page from the tree and we'll look at second derivatives. So we have y is f of x. We have the first derivative, dy on dx, is f dash of x. And then the second derivative, this is the notation we use here, d squared y on dx squared is f dash dash of x. Now, we're familiar with the first derivative. We know that it tells us the slope of the function, okay? That dy on dx tells us the slope of the original function. And in apps of calculus, we'll start to learn more about what the second derivative tells us. But really, it's just the slope of the slope function, okay? That further derivatives just tell you the slope of the function above. So if we're going to differentiate this, first we're going to express it as a power, and now we're ready to differentiate. Just using the power rule. That's our first derivative. And then we'll move to the second derivative immediately. Full marks. So just applying the n, x, and take one rule twice. All right, with example B, you may look at that and you may be tempted to use the quotient rule. We have u divided by v, and we could, that's a perfectly suitable way of doing it. And if you did it, you'd get the first derivative, but then you would need to use the quotient rule again. Because remember, when we do the quotient rule, we still have stuff at the top, we still have stuff at the bottom. So that would be the long way of doing it. And in fact, one thing we've asked repeatedly over previous tests is we've given you a question like this, we've said find the second derivative, you can use the quotient rule, but it's much easier if we try and simplify it using index laws. Now this here, we can simplify using index laws because everything is x and we only have one term at the bottom. So what we can do is first split the denominator. So I'm going to put it like this. Okay. So we've split that denominator and expressed it as its power. And now we'll use the index laws to simplify it. So here we have the top power, take away the bottom power, and the same here. That's going to be 3 lots of x to the power of 1, take away a half, positive half. All right, so what we've done here is we've just expressed the function in a variety of different ways. And now that it's expressed like this, it is super duper easy for us to differentiate. All right, we'll just apply the power rule. X to the 3 on 2 becomes 3 on 2 x to the half. All right, so there's our first derivative. And then we will move straight to our second derivative. Now all of those fractions can be multiplied together and so forth, so it can be we can simplify that to 3 on 4, and that would also be 3 on 4. The negatives can cancel and so forth, but again, differentiate without simplifying, that's absolutely fine. So you can see, once we simplify it, the differentiation just takes one step, whereas if we're using the quotient rule, we have u and v, and we'll have u and v again, it gets awfully complex. So that we know we can simplify this because every term is in terms of x. We don't have any sines or ln's or coses or anything like that, or e's. And we only have one term at the denominator. So we can look at it and we can see we can split that denominator and use index laws to simplify it. Now this skill as well, it pops up when we did simple differentiation in exercise 2b. That's where it first pops up. Okay, you use simple differentiation to arrive there, but now we're just taking it a little bit further. And you will find lots of questions like this in previous tests. Okay, let's move over here. I think we just had a cos of e of x question, or we had tan of e of x, didn't we? So when we have cos of f of x, all right, I might write the rule up. If we have cos of f of x, so this is just the rules we've just learned, it goes to minus f dash of x sine of f of x. Okay, so we know the derivative of e to the x, so we can go straight to the first derivative. It will be minus e to the x sine of e to the x. Okay, that's our first derivative. All right, so there's the minus, there's the e to the x out front, and then sine of function. However, we're required to find that second derivative. Now, in order to do that, we have minus e to the x times sine of e to the x. Minus e to the x times sine of e to the x. So we'll have to use the product rule. All right, and so now we're differentiating a sine of f of x. That'll be f dash of x cos of f of x. Smash it all together. Now this kind of expression here is something reasonably common that we'll get across the next, maybe not this test, but definitely the next test. And when you start to recognise we're using the product rule, we've got e to the x in both terms. A lot of times what you'll be doing is saying, look, e to the x is common here and here. That's something that can be factorised. Okay, so keep an eye out for when things are common. All right, very good. Now let's move on to question 2. I might clear a bit of space for it just so we're not getting so congested. So I might do it above. So we have a quadratic. We have some unknown quadratic. Y equals ax squared plus bx plus c. We don't know these values of a, b, and c, but we do know f of 0 is 3, f dash of 2 is minus 5, and f dash dash of x is minus 4. Yeah. This one here? Here. Yes. Yes. Yeah, good pickup. Yeah, u dash v plus uv dash. Yes. Thank you. Okay. So, yeah, y equals ax squared plus bx plus c. Or, I'll call it f of x, so we can substitute those numbers accordingly. Now, the first piece of information we have, basically when we're confronted with a problem like this, what we want to do is just use all of these bits of information. Okay, so when we're not really sure what to do, it's like use this, and use this. That's going to get you marks, but it's also going to reveal how to solve the problem to you. So if we're told f of 0 is 3, well, I'm going to put that in here. If f of 0 is, it's going to be, and I'll draw it out, I'll do it the long way. All right, well, that's 0, so we already have c equals 3. Just by putting in one of the pieces of information, we've been able to unveil the identity of c. It is 3. All right, we'll move on to the second piece of information, f dash of 2. So that means we need to find the derivative of our original function. So if we differentiate this, it might look a bit confusing because we've got letters instead of numbers, but the same rules apply. The derivative of ax squared will be 2ax. The derivative of bx will just be b. And the derivative of c, well, that goes to 0. All right, so let's use that information. We have f dash of 2 equals minus 5. We'll put that in. All right, here we have minus 4a plus b is minus 5.
Where's the minus 2?
We're putting in positive 2, aren't we? Sorry, been a bit sloppy today. 4a plus b is minus 5. All right, so if we're looking at this equation, I would expect as well, we look at that and go, there's two variables there, there's two unknowns, there's no way I can solve that unless I have more information, all right? You can't solve an equation that just has two variables unless we have some more information about it. So we're gonna have to use this last one, which is f dash dash of x. So when we find the second derivative, all right, here's our first derivative, 2ax plus b. When we differentiate 2ax, we'll get 2a. And the derivative of b, well, b is a number at this stage. The derivative of b is going to be 0. So we have 2a, and we know that the second derivative equals minus 4. That's the last piece of information we have, which means a equals minus 2. Okay, now we can determine the value of b. Well, we have 4 times a plus b will be minus 5. And we'll solve this for b. All right, so we identified the values of a, b, and c just by, what's the process? Oh, this looks tricky. No, we just use the information and it just reveals itself to us. Okay, so trig functions will start easy. Again, we'll be applying the chain rule, the quotient rule, the product rule in there. It just compounds everything. So it starts easy and get more challenging. The same with second derivatives. So probably, definitely today, I think just to start with, dedicate your efforts here. And then because we don't have a lesson for a week from today, there'll be a bit of homework to sort of manage over the next 168 hours before our next lesson. All right, any questions?